be discussing section 1.3 of the textbook. The topics will be solving right triangles through the side angle method, side, as well as talking about angle of elevation and how to solve problems with it. So first, we want to discuss naming convention. Last time, we looked at a triangle, and we had the triangle U, V, W, and we define the angles as such: angle W, angle V, angle U. Well, now we want to describe the sides with precision. So the line segment of WU will equal little v, that is here. Line segment of VW will equal u, that is here. And finally, we have segment VU is equal to little w. This is the naming convention that we'll be using throughout this video and throughout the course. So, what are certain types of problems of the side angle or side? Well, as the side angle may suggest, we know a side, we know an angle of a right triangle. An angle being something other than the right angle. So what does a side angle triangle look like? We have a right triangle. Let me make it slightly larger. And let's call this U, this vertex V, and this vertex W, and we'll have generally two angles given. Say we have this angle here as 40 degrees, and we're given a hypotenuse of 2 centimeters. So in this case, we do not know what W is, or sorry, we do not know what little v is. We do not know what W is. And we do not know what angle this is here, angle W. And that is the information that we would like to solve in this problem. The other type of question that we'll get is the side. And one like these would be, let's draw another triangle. And again, have the conventions of the right angle is U. V, we have no idea what it is. We do not know what angle W is, but we do know what V is, which is 6 feet, and what W is 8 feet. And this U, little u, we do not know what it is. So here's an example of a side. Notice we just have to have two of the sides. I could switch these with appropriate values, and we'd have, again, two sides. And we have to solve for the third side and solve for the angles of the right triangle. I will emphasize that this side angle and side can only work when we have a right triangle. Now, you might be wondering, well, what about an angle? So what if I had something like this? Where I knew the angle, I knew I had another angle of 60 degrees, another angle of 30 degrees, and my vertex U, V, and W. And it might be, hey, I know something about this rectangle. Well, yeah, we know some things about it. However, without a side, the scaling of it is the best we can do. And we'll talk more on that later, but we can't make a certain conjecture on or a certain statement on exactly what the sides are because we don't know any of them. It could be huge, it could be small, but we can talk about in regards to scaling. That's for a future video. What we want to focus on is when we know one side, one angle, like so, and one side or two sides and no angles, much like this one. So this one I should write as a question mark. Okay. So when we have let's solve this question. This will be my first example. So how do we go about this? Well, we want to use our trig functions and we want to try and piece together what information we know. How can we have a trig function that only has one variable in it? Well, we have a reference angle, so let's start thinking about what can be done with that. All right. Well, one of the things that might be easiest is finding the other angle. So we have 90 degrees minus angle V will equal angle W. So 90 degrees minus 40 degrees is equal to 50 degrees. And we found angle W. That's one of our mystery variables. Okay. Well, what about side V? Well, we know that sine of angle V is equal to the opposite over hypotenuse, which in this case, our opposite is angle V, side V over 2 centimeters. Okay, plug in 40, and we want to times by 2 to the other side, and we have little v is equal to 2 centimeters times sine of 40 degrees. And this will equal 1.285575219 centimeters. And because it's an estimation, I'm going to put in about. Now, some of you might plug this into your calculator and you might get 1.4902263,209 centimeters. This answer is wrong. Why? Well, because I'm specifying that I'm using degrees here. And so if you do not have your calculator set to degrees mode, then it will default to radians. So if I plugged in just, if what I plugged in my calculator looked like this, 2 divided by sine of 40, your calculator could interpret that as 40 degrees or 40 radians. It depends on the mode that is in. if you don't know what mode your calculator is, and plug it in as this, whichever one you get. Now you know you're in radians or you're in degrees. We will be using whatever context of the problem is. So if it's in radians, then use in radians. And here we have been described to be in degrees, so I'm going to write it in the context of degrees. With that said, if you can't change your mode, then I could take this and I could transfer it into degrees or radians by using the conversion methods from the prior video. So this is our correct answer for V. Notice I'm keeping my units, as well as I'm keeping my units in degrees here because I want to match what the other side is. What I mean by that is angle V was given in degrees, so therefore angle W should also be given in degrees. All right, so what's the only variable that we have left? We found the angle of W. We found the side length of V. Well, we need the side length of W. So now we can make many different ways of doing this. We could try Pythagorean's theorem. We could do it through sine of angle 50 degrees or angle W. We could do cosine of angle V. And I would argue the most correct answer would be cosine of angle V. That is what we plug into our calculator. We use this reference and build it from here. Why? Because I'm not using any form of estimation. If I was to do the Pythagorean theorem, where I have 2 squared plus v squared equal, or sorry, 2 squared equals v squared plus w squared, I'm going to have to plug this big thing in, but then also I have to square this, and I'm estimating here, denoted by these squiggly lines. If I'm estimating, I'm introducing error. And when I times, I'm just going to compound that error. So it's better to use the given numbers as much as possible. Okay? So when I build this in as cosine of angle V, I have adjacent over hypotenuse, so I have my W, little w, over 2 centimeters. I'm going to solve for W, so I have little w is equal to 2 centimeters times cosine of 40 degrees. And that will equal about 1.5320886 centimeters. That's my little w. Okay. So now we have fully solved the side angle problem of a triangle. So let's look at example number 2. That is this example. When I want to solve for the unknowns, again, I'm going to start with, what do I know? Well, I know Pythagorean's theorem, so we have v squared plus w squared is equal to u squared. My v is 6. My w is 8. And when I have 6 squared, that is 36. plus 8 squared, that's 64, which then we have 100. That is 36 plus 64. And that is equal to u squared. So I square root it, and I have 10 centimeters, or actually I have feet there, equals u. Yes, we took a square root. So might be one person that goes, hey, is that plus or minus 10? We're asking for a real world triangle. Negative 10 centimeters doesn't really exist. At least I can just flip the triangle over if that's how you can think of it or want to think about it. But later on, that notion of what a negative length looks like, we'll explore that concept a bit more. But for now, just take the principal square root, meaning square root of 100. I just want the positive value, and that's 10. And what's the unit? Feet. So 10 feet is u. So going to the next one, we want to solve for an angle. So 10 is an exact answer, so we could use that. You wouldn't be wrong for using that, but again, practice using the exact values given. Don't use one that you calculated, because, for instance, what if you made a silly mistake and you wrote down 11? Everything that you would be doing now, if you solve these with the use of sine and cosine, you'd have a wrong answer. So when in doubt, use the values given in the problem itself. So with that notion, how are we to solve for the angles? Well, let's see. If I write tangent of angle V, that is equal to the opposite over adjacent leg, and the opposite leg is V, little v, and the adjacent leg is little w. Okay. Well, we know what these are. This is 6 feet over 8 feet. And we can just cancel out the feet and we have 6 over 8. So now I want to take the inverse of the tangent. So angle V is equal to arc tangent of 6 over 8. Now, you may or may not have an arc tangent on a calculator. Sometimes you'll see tan to the negative first. That is tan inverse, as discussed in a prior video. But for the nomenclature, we want to have tangent inverse of 6 over 8. And how you can find this, typically if you press the second key and then the tangent key on a calculator, that will be tangent inverse or arctan. Either one of these will allow you to get to the right answer. And this is again where it's important to see whether your calculator is in degrees or radians, because we're going to get a massively different result. So if your calculator is in degrees, you'll see that this is angle V is equal to 36.86989765 degrees. Now, it is important that this is your answer. If you don't have this, double check how you plugged into the calculator. But you might be in radians. Now, we want to give this in degrees because that's what the problem was asking for. or I am requesting that as in degrees for this particular problem. If I request it in radians and we have an answer in degrees, that's not what I asked for or what the problem asked for. So you have to either convert this to radians or put your calculator in the mode for radians and re-plug it in. Okay. So with this as our answer, we come to the final unknown, and that is angle W. We have two methods of solving this. We could go, hey, I know 90 minus angle V is equal to angle W. And we could plug in this number, 90 degrees minus 36.869899765 degrees. However, again, this is an estimated number. We got this approximately because we plugged it into the calculator. So wanting to get an exact answer, I would suggest we do the cotangent of angle V. Why? Because the cotangent is the adjacent over opposite, which is our W over V. So that's 8 divided by 6. And you might look, well, I don't have a cotangent inverse. That makes sense. But remember, we can view this cotangent as tangents of angle W. This equals 8/6. So finally, I have my angle W is equal to tangent inverse of 8/6. So I started with a cotangent of a reference angle, which is really the tangent of the other angle. That is how you can think of these things. If you spotted and jumped straight to here, that is a-okay. That is a fine answer, but either way, whether we use this method or we use this method, we're going to get something that looks like this. The angle of W is about 53.13010235 degrees. Yep. And now we have solved all pieces of the information. All right. So now we're going to talk about angle of elevation. So there are two types of angles to discuss. The first is we want to get a reference. So this is, we're going to call the horizon line. Now, if I was to look straight out, that's where the horizon line is. It's the line of which you're looking at. Surveyors will often use an equipment to do such a thing. And then when I want to get a reference point, I'm going to measure how far do I have to look up, how far do I have to look down to see the top or bottom of any sort of place that I'm looking at. So here, this would be my depressed line of sight. This would be my elevated line of sight. And here, this angle is my angle of elevation. And this angle is my angle of depression. So again, it's how far do I have to look up to see my reference point? How far do I have to look down to see my reference point? Okay. And what would be a good way of doing this? Well, what sort of problem is, say I have like a tower and I have an antenna on top of the tower. I now know that the antenna is 20 feet tall. So when I'm on the ground, I'm here. So here. This angle, say, is 26.6 degrees. And when I look at this angle, that is 32 degrees. How high is the building? Okay. So to answer this question, let us work on the computations. So I want to know how tall this building is. Notice I don't know how far away I am from the building. So I could either solve for that, or we could just we could try and find a system of equations to solve for just the height. Why would I want to do such a thing? Well, I would want to solve for only the thing that I'm wanting to solve. I didn't ask about how far we are from the building. So in the context of a question for a quiz or homework, you don't need to provide that answer. So let's first find out what we do know. Let's draw a picture. And when we draw this picture, we can draw two of them. The first one being the angle is 26.6 degrees. Our height is just y, and our distance I'm gonna label as x. And we know that it's a right angle because we trust the engineers that built this. And so now I can form a relationship between these variables and just these variables and nothing else. So let's call this point here V again and say, all right, what is the angle of V? 26.6 what trig function do I know that I can solve for this? And that would be tangent. That can relate these variables together. So tangent of 26.6 degrees is equal to y over x, opposite over adjacent. What other picture do we have? We have a picture like this, where we have y plus 20 because we have the height of the building plus the height of the antenna. And what angle of elevation did we take to look at that? 32 degrees. Again, we have a right angle, and we're still staying in the same spot. Our view is from the same spot. And let's write up a system like this. Because we're in the same spot, we know we have the same distance of x here. So we're going to write tangent of 32 degrees is equal to y plus 20 over x. So we don't want to solve for x directly, because instead we could take this equation and say, hey, I have x, or I have x equaling y divided by tangent of 26.6 degrees. I'm timesing by x and dividing by the tangent to the other side. So if I have this, I could plug this in for x here and now solve for y. So I'm not actually solving for x in the sense of getting an exact value. I more so found the relationship of it in terms of y, and now I'm plugging that in. So we get tangent of 32 degrees is equal to y plus 20 over, and we have y divided by tangent of 26.6 degrees. We can take the reciprocal of this. So we get y plus 20 times tangent of 26.6 degrees all over y. Let's times by y to the other side. And we get y times tangent of 32 degrees is equal to, and I'm going to distribute this tangent into this parentheses. So we have y times tangent of 26.6 degrees plus 20 times tangent of 26.6 degrees. I'm now going to subtract y to the other side. So I have y tangent of 32 degrees minus y tangent of 32 or 26.6 degrees equals 20 tangent of 26.6 degrees. We can factor out a y from here and here, making this a parenthesis, putting a y over there, and now we can divide by this tangent, and we get y is equal to 20 tangent of 26.6 degrees all over tangent of 32 degrees minus tangent of 26.6 degrees. And when we plug that into our calculator, we're going to get an answer that looks something like 80.69876669 feet. Now, a rule of thumb is a real world question requires a real world result. So if I was your employer and I gave you this question, I wouldn't expect you to give me y equals 80.6987669 feet. No, I don't need that level of precision. Instead, we're going to say the height of the tower is about 81 feet. Spelling is hard. So, this is the answer that I would expect on the homework and or quiz. Okay. So it's important to note that whenever there's a real world question, we require a real world result. Okay. So the last thing I want to go through today is another application problem, as well as more of a step-by-step on how to solve these questions, because we kind of had a little bit of a system, but let's articulate this a little bit more and then solve another type of question. Okay. So there are 5 steps to solving a application type problem. So step 1 would be draw a picture. Step 2 is name/label unknowns. 3, find applicable formula. 4, solve formula. 5, answer with context. Actually, I'll add answer with correct context. What do I mean by this? I mean, if it's given to you in degrees, make sure your answers are in degrees, not radians. If you're given lengths in feet, make sure your answer is in feet. If it's a real world question, then have a real world result. Don't have a 50.21834556, just have a 50 degrees, or sorry, 50 feet. And also make sure that you can add flavoring to that answer. So instead of just leaving it at y equals 81 feet, we put it in a sentence. The tower height is 81 feet. Okay? So for this example, we have a tower, and we know that the angle from the top of the tower to the ground is 35 degrees. We also know that the tower is 100 feet. What is the length of the wire coming from the top of the tower to the ground. What is the length of that wire, and how far is the wire anchored to the ground from the tower? So in other words, we have a tower here, and from the top of the tower, we have a wire, and we know that this angle here is 35 degrees. We know that this height, I'm going to put little h, is equal to 100 feet. We do not know what the length of this wire is. I'm going to label it W for wire. And we do not know what this distance is here. And I'm going to call this like the D because it's the distance via the ground. And this anchoring point, I'm going to call it A because it's an anchor point. So this point up here, I'm going to call it T because it's the top of the tower. Okay. So now that I have this all labeled, I want to start forming relations with what I know and what I don't know. I know the height of the tower is 100 feet. So I want to use trigonometric equations that use the height of the tower, but also this reference angle of 35 degrees. Okay. Well, let's first use this reference of D. Let's try to find that. Well, I know the tangent of angle T is the opposite D over adjacent H, which is 100 feet. So I can write tangent of angle T is equal to D over H. That is my formula. What's another formula that I can pick out of here? Well, I want to find W. Now I want to find W with only the information given in here. I don't want it to be dependent on D. So what can we do? Well, we have sine as opposite over hypotenuse with reference of angle T. That won't work. And we have cosine that is adjacent over hypotenuse with reference of angle T. So that's the one we're going to use. So we have cosine of angle T is equal to H, the height, over W. Now that is my naming convention that I use. Now we're going to start plugging in the different values. So here we plug in angle T, so we have tangent of 35 degrees is equal to D over 100 feet. We times by 100 to the other side, and we get 100 times tangent of 35 degrees is equal to D. And we get 122.0774589 feet equals D. Okay. Over here, we have cosine of my angle T, which is 35 degrees, equals my height, 100 feet, divided by my W, that's the length of the wire. In this case, it's the hypotenuse. We're going to times by W to the other side, divide by 35 to the other side, and we get W is equal to 100 divided by cosine of 35 degrees. And we end up finding that W is approximately 70.077, sorry, 07, sorry, let me restart. 70.02075382 feet. Now, this answer isn't full points because we solved the formulas, but now we have to put it into the correct context of the question. So we can say the wire is about 70 feet. Oh, did I write this down wrong? I did. Yeah, I was looking at the wrong one. My apologies. These values are flip-flopped. I have this is supposed to be my W, and this is supposed to be my D. So this answer goes here, this answer goes here. So my apologies on that. However, there's a very important thing that I will talk about on how I knew that that was an error as soon as I started writing out the context of the question, and hopefully this makes sense. So the wire is about 122 feet long, and the wire is anchored about 70 feet away. Now, how did I know I was writing down something wrong when I did my equations? And probably some of you were screaming at me going, hey, he's doing this wrong. I plugged in my calculator and I got something else. I got that. Well, would it make sense that a 70-foot wire could be anchored away from the top of a tower 122 feet away from the tower? No, that makes absolutely no sense. And so as soon as I started writing it out and I started going through it, I'm like, oh, wait, that doesn't make sense. Not at all. I must have got them backwards. Sure enough, I look at my notes. And yeah, I was looking at W when I was answering for D, and I was looking at D when I answered for W. But that's why it is important to look and make sure that it makes intuitive sense. Kind of the same thing when we were talking about the other one when we had the square root of 100. Well, 10 centimeters makes sense. Negative 10 centimeters makes no sense. Makes no real world sense. So that is why it's always good to write down what the context of the problem is, not only because that's how you can get the maximum amount of points, it also makes you able to check your work passively by going, okay, these numbers make sense, but I had them flipped initially, and that didn't make sense. So today, for your check-in learning, it will be to restate this in your own words. You can copy it verbatim, or if you want to change the verbiage a little bit, that's fine. But just restate the answer to this example of the wire, about how long and how far it is anchored from the tower. That will be a check-in learning. Thank you, and have a great day.